Now we take a magnetic force. Now we go to the other subject, which is a magnetic force on a charge particle. Okay. All right. So now this is number 1 here, how to produce magnetic field. Now number 2, we're going to discuss a magnetic force on a charged particle. I just want to remind you about the electric force on the side here. Remember with me, my son, if you have an electric field like this, in this direction, this is just a reminder, okay, of what we have done before. If you take a positive charge here, Q, you know that there will be a force on the charge with the electric field. So there will be a force in this direction. And that force is Q times E, right? You remember this? That's the electric, I'm going to put here E, which means electric force. If you have a negative charge here, this is a reminder only, yeah? Negative charge Q, there will be a force on this charge in this direction. The force, electric force, is Q times E. Because the charge is negative, the force and the electric field are in positive direction. Because the charge is positive here, the force and the electric field have the same direction. Okay? That's about electric force for a charged particle in electric field. Now we are going to take a magnetic force on a charged particle. Now we have this is called the electric force, Fe. Yeah? Fe here is called the electric force. Okay? On a charged particle. Okay? Charged particle. So here the charged particle is an electric field. Now we're going to take it and put in a magnetic field. Okay? So let's take a positive charge, let's say, okay, for the time being. And this positive charge is moving with the velocity v in this direction, v, okay, all right, and it is in a magnetic field in this direction, b. Let me tell you here on the side here, a vector. Now we are going to work in 3 dimensions. By the way, this problem here is only 1 dimension, right? The force and electric field, they are either in the same direction or opposite. But now we are going to go to 3 dimensions, so we have to have a vector in 3 dimensions. So we are going to show you a vector which looks like this, a dot with a, means it is this direction is outside the board, the board. A vector like this, a vector which shows like this, it means this is inside. This vector direction is inside the board, okay? The board or the paper or... So, because the vector look like this, right? This is a vector. If you look at it from this side, you see this. So this vector is inside the board or paper. If you see this part here, the tip, this is the tip actually, so it is coming out, okay? So, for this you are looking from here, it's coming out, so this vector is coming out, and this vector is going in. This B is actually coming out. So there will be a force, like here, I'm going to call it magnetic force, FB. Okay? It's called Lorentz force, okay? Is equal Q, the charge, V cross B. Be careful, my son, this is very important concept here. Huh? The force is not, this is the 3-dimensional problem now, because we have a cross product here. When you see the cross product, this will give you a vector. But this vector here, which is this vector, the product of 2 vectors give you another vector, which is FB, which is perpendicular to the plane where the 2 vectors are, okay? This is very important, my son. So this is the cross product there. Here, there is no cross product here. So this is the cross product. This here is the cross, they call it the cross product. Or sometimes they call it the vector product. Okay? Which means it gives you the product give you a vector, okay? That vector is a force F. So the force on the charged particle, okay? Fb is the magnetic force, Q is the charge, V is velocity of the particle, and B is the magnetic field. The magnetic field is a vector, V is a vector velocity, and Fb will be a vector, okay? All right. This is important. So it has a magnitude, this vector, this force. The magnitude of Fb is Let's write it down here. Q, V, B. The cross product will give you the sine theta. And theta here, this angle theta actually, angle theta is the angle between V, the vector V, and the vector B, okay? In this figure here, B is outside the board and V to the right means the angle is 90 degrees. You get maximum force when sine 90 is 1, okay? So FB is maximum. That's the value of the maximum value, okay? When the angle theta is 90 degrees, okay? Remember, so sine 90 will give you 1. And FB is 0 when the angle theta is 0 or 180 degrees, okay? Parallel 0 degrees or 180 degrees. Either parallel or anti-parallel. That's the angle between B and V. I'm talking about this angle between these two vectors, okay? That's the angle theta which goes there. Now, so this is the magnitude, okay? Number 1 magnitude of this vector. Number 2 is the direction, okay? Direction of that vector. Direction, you use what is called, use the right hand rule. So my son here, right hand rule. And this rule is always used whenever you are dealing with a cross product. Whenever you are dealing with a cross product, you have to use the right hand rule to find the right direction of the force F, okay? That's the very important. I will show you later how to find the direction of the force, but let's see now. Let's see how we have to use the direction to find the direction of the magnetic force. Here, the direction of the electric force is very easy to find. It's either parallel to the electric field or anti-parallel to the electric field, depending on the sign of the charge. But here, no. Here you have to use what is called the right-hand rule to find the direction of the force. I'm talking about direction here of the force, of this FB, okay? Because generally, V and B are given to you, and you are looking for the direction of the force, which is the cross product of V and B, okay? Now let me quickly discuss with you this idea here, how to find the direction, okay? Now, let's look at this example here. For example, you have this B in this direction, and V, the charge, is in this, the velocity is in direction. What will be the force FB in this case? Okay? My son, what will be the FB in this case here? I want the direction of FB. Of course, in this case, FB is 0. I hope you know why. Because the angle here between the velocity and B is 180 degrees. So sine of 180 will give you 0, so the force is 0. Automatically, the force is 0. Okay? Let's look at, in this case here. This is B. And I'm going to change the direction of the V. I'm going to make it like this. Okay? Upward. Velocity is upward. Can you give me the direction of the force here? I'm going to show you how to use the right-hand rule. Okay? So, in the right-hand rule, you put your fingers with the first vector, which is V. And you sweep. You make a sweep like this to the second vector, and the thumb will give you the direction of the force. Look with me here. My V is in this direction. So you put your fingers in the direction, and then you sweep. You see here, B is in the direction. You go from V to the vector B. If you do like this, it will never take you to B because B is in this direction. So you have to put your hand. You have to put your hand in such a way that from V you go to B, and the thumb will give you. You have to make here 90 degrees here. The thumb will give you the direction of the force. The force in this example here is inside. So the force on the particle will be inside. So I'm going to do like this. This is FB. Okay? And it is a vector. Its magnitude, I can find it, its magnitude, is QVB sine of what here? What is the angle between B and V is 90 degrees, so sine 90 is 1. So here, the force, FB is QVB only, QVB. And if you are given the charge, you are given the velocity, the speed, and the magnetic field, you can calculate this in Newton, of course. Be careful here, my son. This is in Newton. Here, the SI units of this force is in Newton. We know the force is always in Newton, okay? We use Newton for SI units of forces. Now let me show you another example here quickly. Is this one here? So my B is in this direction. I have a negative charge and going up like this, upward, okay? But the charge now, charge Q, is negative, okay? The charge is negative. So what do you think will be the direction of the force? When the charge is negative, like here, you use the right-hand rule, but then you invert the direction, okay? Be careful, my son. I'm going to repeat. You use the right-hand rule, V cross B. You see V cross B? B is to the right, so you do like this. So inside, but because the charge is negative, there will be a negative sign here, you reverse. So in this case, my force will be outward. FB will be outward. So I'm going to repeat for you, my son. If the charge is negative, you use the right-hand rule, and then you reverse the direction, okay? If the force is inside, it should be outside. If it is to the right, it should be to the left for negative charges, okay? You always use the right-hand rule, and then you invert, okay? Now let me give you one more example. If my B is in this direction, let's say B is inside, and my charge is positive, and my V is up, but V is inside. Can you tell me, my son, what is the direction of the magnetic force in this case? Your fingers, your 4 fingers, should be with what? With V. I can do like this, I can do like this, I can do like this, but only one direction will when I sweep, it will take me to B, is this here. Because B is inside, so this is V, B. You see B like this? Now, my force is what? What is the direction of the force? To the left. So the force on the particle will be like this, to the left. Okay? That's the direction of the force. If my charge was negative, and I have the same situation for B and V, my force will be what? In which direction? You use that hand rule, and then you take the opposite direction. My force will be to the right, like this, okay? FB. So here, the force is to the left. Here, I use the same rule, but then I reverse the direction of the force, because the negative charge, there's a negative sign here. There's a negative sign, these are inverted, okay? So this is important to understand, and let's look, so you can have a force of 0, you can have a maximum force here, like here also, okay? This force is this maximum all over the places here, but if you have your magnetic field is like this, you have a positive charge, and your V is in this direction, and you have an angle theta here, it's not 90 degrees. My force, magnitude of the force will be what? Q, V, B, sine of the angle, okay? And the direction of the force, of course, is what? In this case, is inside, okay? V cross B, the force FB will be inside. And it will have this magnitude here. So this is important, my son, to understand these points, okay? So let's write this important concept here, that FB, the force FB as a vector, is always perpendicular. You see perpendicular here? Perpendicular to the plane that contains V and B. V and B, yeah? V and B. Okay? So if my V and B are in this plane, my force will be either out or in. Okay? That's what I mean by here. FB, the force FB, is always perpendicular to the plane which contains V and B. Okay? Very important. The SI units it has SI units, of course, for the B, okay? SI units, I didn't talk about the SI units of B, the magnetic field, is Tesla T. There's another units which is not the SI units, the Gauss also. Okay? There's another units, the Gauss, and one Gauss, like this, G, yeah? G, the letter G, yeah? One Gauss is 10 to the power minus 4 Tesla. Okay? The Earth has a magnetic field, okay? The Earth magnetic field, and it has a lot of application, okay? The magnetic field of the Earth is about 0.5 Gauss, which is 0.5 and to the power minus 4 Tesla. It is weak, but it is useful in some instances. Maybe we'll discuss them later, inshallah. Okay, let's look at some properties of F, the force, the magnetic force, FB, which is a magnetic force. Okay. The first thing important is that the force FB has no component along the V, direction of V. Because I told you, FB is always perpendicular to the plane which contains V and B, and therefore it doesn't have any component along the direction of the velocity, and therefore cannot change the speed of the particle. It cannot change. The speed of the particle in these problems is going to be constant. You might change only the direction of the velocity, but not the speed. FB cannot change the kinetic energy because of the first here, okay, property here. If the speed doesn't change, the kinetic energy will not change of the particle. The kinetic energy of the particle in this problem will be constant. FB cannot do work on the particle. Why is that? Because kinetic energy is constant. Because what is the work? The work is a change in kinetic energy. If the kinetic energy cannot change, so that there will be no work. FB can accelerate a particle only by changing its direction. And we will see this in details after a few minutes, okay? So this is important regarding the properties of this force. Now let me show you some properties of the magnetic field, okay, itself. Remember we draw the permanent magnet, okay? So if we take a permanent magnet with north and south, you produce a magnetic field, and let me draw the magnetic field lines. So they enter here, because these are vectors, and they come out from the north pole, okay? So they do like this. They come out from the north pole and enter the south pole of the magnet, okay? All right, so this is the north pole and the south pole. If I take this magnet and cut it into two parts, so I get another north-south, and this part will be north-south, okay? If you take this magnet again and cut it into two parts, you get north-south and north-south, and so on. And you keep doing this, you can never have what we call a monopole. Monopole, which means a pole with only either north or south pole, only a piece of magnet, it has only the north or south pole. You cannot have that, okay? Not for the charges. Electric charges, you can have a positive and negative, you can separate them, but here in magnetic field, in the magnets, you have always north and south, okay? You can never have a monopole. We always have a dipole, which is north and south. The other thing is that if you take a magnet north and south here they attract, okay? Attract. So there will be attraction, okay? If you take a north and south with the south and north, here, unlike poles, they attract. So you have to write unlike poles attract, and like poles, here there will be a repulsion. I'm sure you tried this with magnets. You try to bring magnet close. You notice that some of them sometimes they repel and sometimes they attract. They attract in this situation when they have unlike poles. If they have like poles here, like poles, they repel. Repel. They repel each other. Like poles repel. Same thing when you have south north and north south like this. These two they repel, and the previous one they attract. So this is important regarding properties of the magnets and magnetic field. So the magnetic field, they are like this they close on each other, okay? So they close like this. So they come out from the north, they go into the south pole, and they do like this, okay? North and enter the south pole. Okay, my son, before we start the new concept of cross field, I just want to check with you if you know how to find the direction of the force FB in these three examples, okay? Here we have a positive charge, okay? The charge in the first example here is positive charge, Q, another positive charge here, and the negative charge is here. Remember, to have a magnetic force, you should have a charged particle and it has to be moving. Okay, because the force, if you remember, FB is equal Q, the charge, V cross B. So, if you have a neutral atom or neutral particles, neutral means Q equal to 0, there will be no force on it. Even if it is moving in magnetic field, there will be no force. So you need the force, you need the velocity which is moving in particle, and you need the magnetic field to have this FB. Three things you need to have. So we have the three things here. We have the charge, magnetic field, and V. Charge, magnetic field, and V. Charge, magnetic field, and V. Okay? All of them. And I need to know the direction of the force by using the right hand rule. So I'm going to check the right hand rule because it is important to know it. So you open your hand like this. Your fingers are what? Are with the first vector in the equation, which is V. And then you sweep your fingers toward B. And the thumb will give you the force F. So let's see here. So V is like this, okay, you can see, and B is up. So this direction is actually outside. I'm showing this on the board. I hope you understand that this vector, this direction is outside. Okay, so V cross B will give me the force outside. So my force in this case here is in this direction, F B. Okay, that's the direction of the force in this case. Okay, this means actually it is outside, okay, because this is the third I'm trying to show here three-dimensional on a plane, but I hope you understand that it means outside, okay, outside the board, okay, that's the force. If my charge was negative, you do the right hand rule and then you invert the direction to be inside, okay. Give me the direction of the force in this case here, okay. V is outside, so you put your fingers outside, so you come like this, outside. The B is to the right, so you see like this. V is outside, that means outside. B is to the right, and the force will be up. So here, the force is up. That's the direction of the magnetic force. Of course, the magnitude you can find. You know how to calculate the magnitude. Okay, let's look at that the last example there. Okay, V is like in this direction. Okay, I can do like this. I can do like this, but when I do like this and I sweep, it doesn't give me, it take me to B because B is outside. So you have to do like this. V cross B, you see? V cross B. So the force is what? To the right, but because negative charge, the force will be to the left. So that's my force FB. I hope this concept of finding the direction of the FB, the magnetic force, using the right hand rule is clear. Now you go and practice, my son, with your right hand rule. Don't be careful, don't use the left hand rule. The left hand rule will give you the wrong direction, okay? It will give you the opposite direction of what you are looking for. Thank you.